So today I'd like to talk about how you would do a proof of type safety using logical relations. So yesterday we talked about strong normalization for the simply typed lambda calculus, that are all terms, well-typed terms in the simply typed lambda calculus terminate. Today, I'm going to start by showing you how you would prove type safety for simply typed lambda calculus and then extend that language to be non-terminating. In particular, we'll add recursive types in the second part of the lecture, and then see, how our proof technique, our proof method of logical relations extends, needs to be tweaked essentially in order to accommodate a non-terminating language. Okay? All right, so that's the plan. So let's start out. What is type safety? Sorry, louder?
Type safety means that if you can find the type of the term, then you can erase it and receive
Okay, so it terminates in this language because we're going to talk about simply typed lambda calculus. But if you had a non-terminating language, the slogan that we use for type safety is simply, if a term is well typed, then it won't get stuck, right? Or that it, or rather, Milner's famous slogan is, well-typed programs do not go wrong, right? That is a famous slogan. And of course, well-typed programs do not go wrong. Of course, now that begs the question, what does it mean to go wrong, right? So it's a rather general statement that's meant to intuitively capture what we mean by type safety. But in general, we would then need to formally say what is our notion of going wrong mean. So in particular, what we're going to talk about is you have a certain operational semantics. If you have a well-typed closed program and you start using the operational semantics to evaluate the program, you will never reach a stuck state. And what is a stuck state? Where you can't take an additional step. But, so whenever you do reach a stuck step, whenever you become, unable to take one more step, you should have you should basically have a value in your hand, right? You shouldn't have some sort of situation where you have a number 5 being applied to, let's say, true, right? That is an application that's going to get you stuck, right? Okay, so let's formally state type safety over here. Basically, we want to say that if E is a well-typed closed program, typed out, and suppose that E takes some number of steps. This is not the transitive closure. I just mean some number of unspecified steps to get to some other program E prime. Okay? Then one of two things must be the case. Either we already have, either E prime is already a value. I'll write that as val E prime. Or another step is possible. Or there exists an E double prime such that E prime can take one more step to E double prime. All right? And now here, of course, I'm using a small step semantics, right? Just like I was yesterday. That's what I mean by this single extra step, right? Okay. So that's the formal notion of type safety, the way we stated. Is this surprising to people? Have people seen? It is surprising to people. Tell me why.
No, I was just asking I haven't seen it.
Oh, you have seen it before. Okay, perfect. All right. Okay, so how do we generally prove type safety? What have you heard? Progress and preservation, yes. Everyone has heard that we prove type safety using progress and preservation. All right, so let's state progress and preservation. I just want to make one thing kind of clear here. So progress and preservation is a technique for proving type safety. It should not be considered the statement of the type safety theorem. Progress and preservation on their own should not be considered the statement of type safety. All right, type safety is still what's up on the board, that well-typed programs will not get stuck. Right? It's a little distinction to make because it's about having different proof methods to prove this statement, because that's the statement of interest. Yes? Let's come back to this in just 1 second. I'm going to write progress and preservation up on the board. Okay, so how do we normally prove it? Well, we have a progress lemma. that says if E is well typed, then it can always take another step. There exists, it's a value, or then it's a value, or there exists an E prime such that it can take another step. That's progress. So if it's well typed, either it's already a value or you can take one more step. Yes, Adam?
Just in case it wasn't clear, I wanted to say again, these concepts have not been presented previously at this course.
Okay, all right. How many people have heard of progress and preservation? I need to get a poll. Okay, I think I'm kind of safe then. All right? Good. And even if you have only heard of it, consider this, I'm not going to show you how to prove progress and preservation, but we are going to talk about the statement, and then we're going to see how to prove type safety using logical relations. All right? So I'm glad like most people, almost everyone has at least heard of it. Okay, so that is progress. A well-typed program is either a value or it can take one more step. And let's put down preservation. What does preservation say? And in a moment, I want to compare the statement of progress and preservation with the type safety theorem that we've stated up there. Right? Okay, so if preservation says that if a program is well typed and it takes a step, E steps to some E prime, one step, then that new program E prime is well typed. And in fact, has exactly the same type tau as the original program E did. The preservation lemma is also referred to as subject reduction. Okay? So, let's take a look. So, progress and preservation, as compared to our type safety theorem, right? Our type safety theorem is saying no matter how many steps we take, either we have reached a value or we can take one more step, whereas this is talking about one step at a time, right? Preservation are really sort of focusing your attention on taking one step at a time, right? And so how do we use progress? Once we've proved these, I won't prove them today, but once we have proved these, how do we prove type safety? Can we sort of...
On the evaluation.
By induction on the evaluation, right. So even if we sort of talk about this intuitively, right, we start out saying, okay, E has some type tau, it takes a bunch of steps to E prime. Well, now we want to show that either it's a value or, so if we do induction on the number of steps that we've taken so far, right, we know that with every single step via preservation, we are preserving the type of the program, right? And then progress tells us that wherever we are, we have a value or we can take another step, right? So there's sort of this ping-ponging, if you will, in a sense, and essentially that's going on between progress and preservation in order to give you the statement of type safety. And that's an intuitive statement, not a literal proof method one, right? Because these get you to this point, sort of taking turns. All right. Okay, so that's progress and preservation. And just before I go on, progress will be proved by induction on this typing derivation. If you want to see how it's proved, I would refer you to Benjamin Pierce's Types in Programming Languages, TAPL. And preservation is proved by induction. It's better proved by induction on the step relation there. So again, Pierce has a nice exposition of how you prove that. All right, so that's progress and preservation. We're going to use logical relations today to prove type safety for the simply typed lambda calculus. So how would we do that? So as I said yesterday, type safety is a unary property, so we're going to set up a unary logical relation. Now I'm going to do something different from yesterday. I'm going to change notation on you. And this is very intentional because I think that the deep sort of intuitions that sit in this logical relations proof method, I want you to be able to see the deeper intuitions rather than get hung up on notation. So I want you to see different kinds of notation for it, all right? So, and also, the notation we're going to use today, you'll see, is a bit more succinct as you scale the language up with, more interesting features. All right, so here's what we're going to do. So remember yesterday we talked about defining a logical relation like this. We want to define a unary logical relation or a logical predicate that says E has a certain property of interest at the type tau. E has a type tau and has a certain property of interest. Okay, today I'm going to, so this was a way of writing, when do expressions of a certain type have the property we want? I'm going to divide this up into two categories. I'm going to first say, when do values of type tau have the property we want, which today is type safety, and then I'll do when do general expressions have the property we want. Okay, so I'm just going to have this distinction. Values versus expressions are just going to make our lives a little easier. Okay, so here's the notation I'm going to use. I'm going to define the value interpretation of a type tau. This is the general form of the relation I'm setting up, so let me just show you the form first. So think of interpreting types as sets. The V means there will be sets of values, and later we'll have an E relation, which will say same thing for sets of expressions. So I want to say that the value interpretation of a type tau is something, all right? I want to put, say, some values have our property of interest. And in general, whenever I write these V relations for my different types in a minute, I will always assume that this value is a closed value, and it has this type tau that is sitting over here, all right? And then the rest of the relations we define will obviously have some extra conditions. But this is the general form that I am assuming for the relations that, for the sets, type interpretations that I'm about to set up. Okay? So for every type, we're going to say, what are the values that belong to this type and do not get stuck when we run them? Okay? So, let's start. We're going to define this just like yesterday by induction on the types. So right now we have two cases. We have Booleans and functions. So let's start with Booleans. What are the values of type bool That's easy. All right, and I already said I'm not going to repeat the typing thing. All right? Let's just assume it for every single one of these. All right. What are... So did you notice when I said, what are the values of type bool, and then I sort of abruptly stopped? I wanted to say, what are the values of type bool that do not get stuck? They're values, so that was trivial to answer, right? Okay, but we're going to have to work a little harder when it comes to functions. So what are the values of type tau1 arrow tau2 that do not get lambdas? Okay, right there. In particular, it's going to be lambda x colon tau1 to match our argument there, dot e. So when do these lambdas belong to the type tau1 arrow tau2? In particular, we want to say that they belong if when you run them, they do not get stuck. Say that again? Right, so we want to say something about the body of the lambda, right? The E has to evaluate to a value, but E can't evaluate to a value because it has this x open in it. So how do we do something about the x?
For all x in the value interpretation of tau1.
Okay. For all, I'll call it V instead of x. For all values, you said, in the value interpretation of tau1. Tell us in English why you said that.
Because E is an expression that depends on x. You can give it some x before we get a value.
Right. So we want to say, give me an argument. And give me an argument of the right type that has the property of interest, just like yesterday. Right? We did this yesterday in an analogous fashion. We were defining Sn of tau1 arrow tau2. Okay? So for all, if you give me some value of type tau1, then if I substitute that value into the body of this lambda, that expression is going to be well behaved, have our property of interest. That's E because this is an expression at the type tau2. In other words, read this as that expression will not get stuck, and we'll define this in a second. Okay? All right. So we're doing exactly what we did yesterday. We have to say something stronger. You know, this already terminates. It's not stuck. But we have to say something about the body, and the only way we can say something about the body is by saying, okay, for any possible argument that you give me, as long as that argument has the property of interest, right, is in the interpretation of, is a valid thing in the interpretation of tau1, which to us now means that it won't get stuck, right? That it's type safe somehow. That's how we're defining these sets. That's how you should read them in English. All right. Okay. So if you give me something that is type safe, that's tau1, then I will substitute that into the body of my lambda, and I will get something that is type safe that won't get stuck. That's how we're building it. Okay. So that's my functions. Now, I promised you E tau. So, these are my value interpretations, and this is going to be my term interpretation. So now I need to say, when do expressions of type tau, and here I'm going to assume that E, here I'll explicitly write it, but it's similar to that. I'm going to assume that E is a closed expression, has type tau, all right, syntactically speaking. So when does an expression belong to our set? And remember, our set is trying to say that it won't get stuck. What should I say there? And if it reduces to something in the set V, okay. Let me try to say something just a little weaker than that, right? Because if we say it reduces to something in the set V, then we essentially have strong normalization, just like we did yesterday, right? We're sort of very, very explicitly saying every single term that is well typed will in fact terminate. I want to do type safety today. We could totally do that and still get type safety, but I want to make my condition look more like the type safety property, which is up here, right? We're after this concept that if you run a term for some number of steps, or rather, let's say, if you run a term for a bunch of steps and get to an irreducible state, then that irreducible state has to be a value. That's basically what we want to say, right? So, let me put the definition of irreducible here. I'm going to write irreducible E as an abbreviation for there does not exist any E prime such that E can step to E prime. Can't take another step. All right, so here then I'm going to say that for all E prime, such that E in some number of steps gets to E prime, and E prime is irreducible. So if you have reached an irreducible state, then that must be a value. Of the right type. So notice this is saying it must be a value and it's type safe itself. That again handles the situation where, if we get down to some value of function type, we want to know that the body of that function is going to be good as well. It's going to behave in a type safe manner as well. Okay? Please feel free to ask questions.
Should I use that the set that we define is actually a set?
Good question. Okay, so that's a great question because I was emphasizing this yesterday. We are defining this set by induction on types, on the structure of types. So let's check. So the definition of V bool never uses the definition of V, the V relation. V tau and our tau 2 uses, refers to our value interpretation of types, but only for smaller types. Tau 1 and tau 2 are each smaller types than tau 1 and tau 2, just like yesterday. So now, but there's a little subtlety. Today I don't have V of tau 2 here, I have E of tau 2. So that should worry us a little. That's why it's, less easy to see today than it was yesterday. Okay, so we're okay with this because V of tau 1 is a smaller type than tau 1 over tau 2. But this E of tau 2, how do we know that E of tau 2 isn't doing something else? So let's go check that. So here, we want to keep in mind that we're referring to E of a smaller type. And what's the E definition doing? It's saying, it refers to the V relations but at the same type. It's not getting bigger. So you see the net effect is, if I take this entire definition of the E relation and inline it right here, essentially, what do I get? I will get a V of tau 2 right there. That means that we're good. We are well-founded. The types are getting smaller, right? This separating into V and E is just sort of a notational convention for making your definitions more succinct, really, overall. Okay? But that's a great question, and that's something you should always check when you set these up. Yes?
If we reach a point and we cannot go ahead, then it must be a bad.
When we reach a point, yes, I am kind of using classical reasoning. And you'll see later on that we do end up doing a classical bit. Like when we do the proof that this logical relation implies type safety, we'll do exactly that. So hold on. Okay, good? All right. Okay, so just like yesterday, yesterday our SN relation was on closed terms. Whenever we set that up, E was always a term that is closed. Didn't have any free type variables. But then we saw that the theorem that we needed to prove, so today the theorem that we need to prove is again, overall about closed terms. Just like yesterday. Yesterday's strong normalization was also about closed terms. But then we went through the reasoning, right? We said, okay, let's try to prove the theorem of interest. Yesterday was strong normalization by induction on the typing derivation. And immediately we hit lambda and we said, oh, we can't do this with a closed context. So we have to generalize the statement of the theorem so that we can talk about some E that is well typed under an arbitrary gamma. We're going to do the same thing today, all right? Basically, we won't directly be able to prove something like, okay, let me back up for one more second. Remember yesterday I had a theorem A and a theorem B, right? And it basically looked like this. We said that if E is well typed, then it is in our SN set or relation. And if something is in SN, then it terminates. We had this two-parter yesterday, right? By analogy, today we have a two-parter too. It looks like if E is well typed, then it is in the E relation. Okay? And if something is in the E relation at the type tau, then it is, let me write it as safe. I'm going to define one more abbreviation over here. A term is safe if it is, if for all E prime such that it steps in some number of steps to E prime, and E prime is irreducible, then, no, actually let's make it look more like type safety. Then either E prime is a value or you can take another step. Notice that looks very much like what I had up for type safety, right? I'm just trying to define it as a predicate so that I can refer to it more succinctly. Yes?
Is there a reason why in the definition of E we don't use the same sort of disjunctive on the right-hand side of the implication formulation?
Right here?
Yeah, why we don't just say if E steps mostly E prime, then either E prime is value, or then either E prime is value, or then either E prime steps or E prime is only no value.
Is there a reason? Let's come back to this question at the end.
Okay.
Okay? Because, I mean, you're right in observing that we are trying to get from, this property to this property. That's exactly what part B says here. I think it would make things a bit messy, at the very least, but yeah. Okay, so just like yesterday, we're trying to split, we're trying to prove type safety today by doing these two theorems. Okay, so yesterday I said that the proof of the first part is hard, and the proof of the second part should trivially fall out from the definition. Okay? We'll see that today as well, but I need to do a little bit more build-up before we can get there, or I'd like to do a bit more build-up. So about that build-up, part A. So as I just said, we won't be able to prove this for closed terms because of lambda, because of the lambda typing rule. All right? So just like yesterday, we need to have this follow as a corollary of a more general statement. And that general statement is the theorem that we will actually prove. And it will have to say something like, if E is a well-typed open term, then go ahead and close it off and make sure that the closed term is in the E relation that we've set up. But today, I'm going to do that in a slightly more, I'm going to again use slightly more succinct notation to do that. So read this as, if E is a syntactically well-typed term, it is syntactically well-typed, it has type tau under gamma, then I'm going to define this notation. E is a semantically well-typed term, and we will define that to mean that it will not get stuck. All right? Okay. So let's do that. So yesterday when we tried to talk about, how do we, we need to close off our term before we can say something about it being strongly normalizing. The first thing we did is we talked about what substitutions are valid. What substitutions can we use to close our term? So I'm going to do exactly the same thing again. But today I'm going to define this G interpretation of gamma. So just like I'm doing interpretations of types here, now I'm doing an interpretation of a type environment. Okay? But let me define this inductively. So for an empty gamma, the interpretation is going to be just an empty substitution. For a non-empty gamma, we are going to say that set contains substitution little gamma, which will correspond to this part, extended with x maps to a value. Okay? So again, assume that x does not appear in the domain of this little gamma, just as x here does not appear in the domain of this big gamma. All right, that's my convention. Erase here. Then, sorry, not then. When does this substitution belong to our interpretation, which is, again, trying to say something about type safety? Well, when gamma belongs to G of gamma, and the value that we have just added to our substitution, V, that belongs to our value interpretation of the type tau, where tau is exactly this type tau here. So I did this yesterday. I did this part yesterday by defining little gamma satisfies big gamma. That is exactly what this is. Modulo notation, right? And it's capturing the same concept. We want to say, what are the set of good substitutions that we can use to close off our term E here? They have to be substitutions whose range contains values that are good values. And now that means they need to belong to our V interpretation of types, our value interpretation of types. Okay? Because that will ensure that they're good values in the sense of type safety. Okay, so with all of that, I'm going to we now are ready to define what this semantic type safety thing is. Okay, so basically it's going to say, give me a good substitution that belongs to my G interpretation of this type environment. And if you give me a good substitution, then I can use gamma to close off E, and the resulting expression, which is now a closed expression, will belong to my E interpretation of the type tau, which we have already defined to mean safety.
Sorry.
Yes?
I don't mean to be busy, but can we get with them closing brackets you're saying?
Ah, absolutely. Thank you. No, it's complete. Thank you. Okay. So, what have we done to set up our logical relation? We first gave the value interpretation for our types. At the function case, we needed to say when do expressions behave in a safe manner. So we did that. Then we needed to define what it means for open terms to be type safe. But here, we're not just trying to define a syntactic notion of type safety using the typing rules. That already exists, right? It's up there. We want to say that that syntactic notion implies a semantic notion which says that this term, when run, will not get stuck. Okay? And so that's what this is capturing. So read this as syntactic type safety implies semantic type safety. More generally, this form of theorem for a logical relation is called the fundamental property of the logical relation. Historically, it's been called the fundamental property or basic lemma. You will see one of these two terms in the literature. every logical relation comes with, you know, the most important theorem you must first prove about a logical relation after you set it up is something known as the fundamental property. And soon you'll start to see the pattern as to what the fundamental property needs to look like. Okay. The theorem that we proved yesterday was the fundamental property for that logical relation. I just didn't tell you that it was called that. Right? Okay. All right. So, and once we have this, obviously this will imply that if it's a closed term, then, you know, it's in the relation. But that should be clear. Okay. So, now that we have this, we're going to do two things. Remember the two theorems we want, theorem A and theorem B, right? So this is a stronger version of our theorem A, that if something is well typed, then it's in our relation. And then we have the other theorem, part B, which was if something is in our relation, then it should imply type safety. So, which one should we prove first? Let's prove B first. And then we'll come back to proving the fundamental property. So I'm going to leave type safety up there. And now we want to prove what I was calling B before, that if something is in our logical relation, a closed term, then it must be safe. And safe is up there, right? And you can already see that, this type safety theorem up here, it's saying nothing other than if E is well typed, then safe E. I could erase everything from and onwards and just replace it with then safe E, correct? Do a pattern matching. Okay, so that's what I have up here, right? This is, this put together with the fundamental property would give us exactly type safety. So let's see if being in the logical relation does in fact imply that the term is safe, that it won't get stuck. All right, how do we do this proof? So we want to show that our closed term is safe. Let's look at what safe says. Safe says for all E prime such that E steps to E prime. So the first thing we'll do is say suppose that E steps to some E prime. Then we need to show that that E prime is either a value or it can take another step. Right? That's what we need to show. Now I'm going to do my bit of classical reasoning. I'm going to say, okay, well, we've reached this E prime. Either this E prime is irreducible or it is not. You guys good with that? All right. Either E prime is irreducible or not irreducible. Okay? So, if it's oh yeah, absolutely. It's not. This is fine. This is not actually classical reasoning. You're right. Yeah. Okay. So either E prime is irreducible, or it's not. All right. If it is irreducible, what does that mean? Or no, rather, let's do the other one first. If it's not irreducible, what does that mean? So case, not irreducible, E prime. Therefore, I erased irreducible. I shouldn't have done that. Irreducible says that you can take one more, that you cannot take one more step, right? So not irreducible says, okay. So if it's not irreducible, then that means we can take one more step, right? So that means that there exists an E prime such that, yeah? Okay. So that means we've just shown this, the second disjunct, so that's good. Now let's work on our other case. Suppose that E is irreducible. Then what happens? Okay, well now we're going to have to work a little harder. It's irreducible, so it better be a value, right? Because otherwise, we won't have type safety. So let's look at our premise. Here it is. We know that E is in our logical relation, what I've been reading as semantically type safe, right? Okay, it's in our logical relation. Well, all right, let's go and use that. So from E colon tau, semantically, what do we know? There's the definition. Well, now our gamma is empty, so we don't need a substitution. An empty substitution will suffice, and therefore what we get from that statement is that E is in our E relation. So from that we have that E belongs to E of tau. Correct? Okay. And now let's read the definition of the E relation. It says that for all E prime, such that E steps to E prime, and irreducible E. Oh, okay, so we can plug into this definition exactly the E prime that we have here. Correct? Plus, in this case, we know that that E prime, sorry, this should be prime, is irreducible. Right? So we know that we have an E prime such that E steps to E prime and it's irreducible. Therefore, we can conclude that that E prime, the same E prime we have up here, is in V of tau, from the definition of E tau. Right? And being in E of tau, V of tau means it's a value. That's what we wanted. We're done. Therefore, E prime is a value. Okay? So it's the same lesson as yesterday. We built the logical relation to capture the property of interest. Okay? And therefore, we were then able to say, okay, if something is in the logical relation, then it gives us the property we want. Yes?
Why do we know that talk about gamma?
Ah, good. Yes, I hand-waved that. So if we look at this definition, which is up there, right, it says we need to instantiate that with a gamma. Use an empty gamma. Use an empty substitution, right? So technically, I should have said over here, instantiate this thing with gamma equals empty. Therefore, we get empty gamma applied to E is in E of tau. Correct? I did that quickly. And then empty substitution applied to E is, of course, E. So that's how we get back here. All right. Yes. Oh, yes. Oh, we're back to the classical thing again.
Here it is for syntax. You have your evaluation for as you find. And just look at the syntax there and you can decide that
Yeah.
Yeah.
You can prove it by induction on E, and E otherwise we can talk.
There's your answer. Okay. All right. Okay, so we just did part B, all right? And part A is the fundamental property of the logical relation, right? But now at this point you should be convinced that if we can prove the fundamental property that syntactically type safe means semantically type safe, then we are done. We have a proof of type safety, right? So let's do some of the cases for that. I'll do one, and I'll leave the other one as an exercise for you. So yesterday, we did. Say that in a second. Okay, what are we going to? Okay, so we want to prove this theorem here, the fundamental property. How are we going to prove it? By induction on? Oh, come on. There aren't even two choices. What? By induction on the structure of the derivation? Yeah? Right. Okay, so theorem, fundamental property. Okay, so we're going to prove this by induction on this derivation, right? And that again means that for every single typing rule that we have one case, right? Okay, I'm not going to do the easy cases like true and false. I leave those to you. We did those for strong normalization yesterday. And if you push through the definitions, you should be able to complete them in a similar manner. So let's do lambda. Again, we did lambda yesterday too, but we did it at the end quickly. So let's do lambda today. So the case we're considering is where we have lambda x colon tau 1 dot e, type tau 1 arrow tau 2, and here's the typing. All right, let's push through this, all right? It's going to be a matter of unrolling definitions carefully. All right, so first thing that we have to show is that. Well, let me write that. Show gamma lambda, sorry, with a double turnstile here, tau 1 dot e at tau 1 arrow tau 2. All right, let's read the definition of that judgment, right? What does it say? It says for all substitutions. So first we have to say, suppose that I have a good substitution. Suppose that I have a gamma, little gamma, that satisfies my environment here. I'm just unfolding the definition up there. And then I have to show that gamma applied to our lambda, our term here, belongs to E of the type. E relation at our type now, tau 1 arrow tau 2. Right? Is there a scribe today? You're the scribe? Okay, all right. I know everyone's taking notes, but maybe rely on the scribe a little more. Because it makes it harder to follow. Yes?
I was just trying to find the same thing I am. You wrote ATM applied to interpretation of ATM.
G, yes, thank you. Okay. All right. So that's what we have to show. Now, just like yesterday, let me push this substitution in. All right. So showing this is equivalent to showing, and again, let me do it a little slowly today. So notice that this substitution gamma, it's going to have the same domain as this big gamma, right? And we're assuming that x is not in the domain of the big gamma, therefore it's not in there. Therefore, it's completely safe to push that in. Okay? So we need to show that this lambda belongs to our E relation of the type tau 1 arrow tau 2. Okay, so that's what we need to show. So now let's go and see what we need to do to show such a fact. Let's read the definition of the E relation. It says that the thing has to be well typed. I'm going to appeal to the substitution lemma for types and say that we can easily show that. I won't do it. Okay? Next it says that if our term, this lambda, steps to some E prime that's irreducible, then we have to show that that E prime is in the V relation at this type tau 1 arrow tau 2. All right? So we say, suppose that our lambda, x dot gamma E, steps to some E prime, and that E prime is irreducible. Now we have to show that E prime is, in fact, in the V relation at tau 1 arrow tau 2. Okay? What do you want to do next? What does this mean? What is E prime? E prime is? It's the same thing because we have a value on our hands. It can't take any steps. Therefore, this number of steps here has to be 0 and E prime. So since this is a value, E prime is equal to exactly the lambda that we have, right? So our proof obligation is simply to show that this lambda, right, therefore suffices to show that our lambda, gamma E, belongs to V of tau 1 arrow tau I didn't do anything terribly interesting. I just noted that I already have a value, and it is that exact value that I have to show is in the v relation at tau 1 or tau 2. Right? Okay. Now, so this is what we have to show. STS suffices to show. All right. In order to show this, we have to go read the definition of the v relation for function types and see what it's asking us to do in order to show that fact. So, what is it asking us to do? It's saying you get to suppose that you have a valid argument that belongs to v of tau 1, and then you have to show that when you substitute it, you get something in e of tau 2. All right. So, we get to suppose that we have some v that belongs to v of tau 1. Right? So, we're working on showing this. We're just expanding out the definition. Suppose that we have an argument in v of tau 1 as per that definition, and then show that when we substitute that v into the body of this lambda, so gamma e with v for x, that term belongs to e of tau 2. Yeah? Okay. Now, where should we go next? How many people worked out the proof of for lambda yesterday? It's analogous. So now maybe we should, we're trying to show something about e with v for x, right? We need some sort of fact about our e. This is a good point to go and say, hey, maybe we should spell out what our induction hypothesis tells us about e. All right? So, what does our induction hypothesis tell us? It tells us that, well, we know that E is syntactically well-typed and has type tau 2 in this environment. Therefore, it tells us that it is semantically well-typed. So from that premise, by applying the induction hypothesis to that, we get that E is semantically, it's in our logical relation. Okay. So now we can go ahead and try to leverage this definition to make progress. But what does that say? So we're trying to use this. This tells us that we need to, if we could instantiate this statement with a substitution that maps, the stuff in gamma and x to something, then we'll know that, we can close off our term E and know that it belongs to the E relation at type tau 2. Right? Okay, so what are we going to instantiate that with? So we have this fact. We're going to instantiate that statement with some gamma. What substitution are we going to use? It needs to be a substitution.
Gamma extended by x maps to v.
Right. So gamma extended with x maps to v, because v is precisely the argument that we have in our hands right now in our proof. Right? Okay, so we instantiate it with this, and before we can continue, we have to show that this belongs to the G relation at gamma x colon tau 1. And that's very easy to see. We know that our gamma belongs to G of gamma. We had it right here in the beginning. And we know that our V belongs to V of tau 1. Those two facts are exactly the thing if you look at the definition of G up here. Those two facts are exactly the thing that we need in order to show this statement right here. And now once we've shown this, right, so we instantiated this with our substitution, we've shown that. Therefore, we get to conclude that when we apply this substitution to our E, we get something that's in the E relation at type tau 2. Right? Here's what we had to show, and that's what we have come up with. Notice that this is the same as applying the substitution to E and then substituting V for X, which is exactly the thing we were after. So we are done. Okay. I won't do a whole lot more proofs on the board, but I like to do them on the board in the beginning because, you know, you get to see, it's this process of looking at the definition, seeing what you have to prove next, saying, suppose I have this, then I have to show that, and just, it's mechanical as a proof should be. All right? Okay. I'm going to leave the next case, the next interesting case, I should say, for you, the case for application as an exercise. And please, it doesn't have to be here. You know, you can do this after the summer school, but you have to work through proofs for a logical relation. Otherwise, you can't ever really understand what a logical relation is doing. It's just one of those things, right? And something else to do is just try to tweak the definition a little bit, change it a little, and see if you still get your proofs to go through. Right? Tells you something about, yeah, why they're defined in a certain way. Okay, so we've done one case of the fundamental property. The other case is basically proceed by induction, and we have therefore finished a proof of type safety for the simply typed lambda calculus. All right? Okay. Here's what I'd like to do next. We're going to add recursive types. Now, I don't think anyone has really introduced recursive types at the summer school. At least that's what. Yes? No one else. Okay, good. So that's what we'll do next. This board. Oh, by the way, actually, before I go on, let's do one other exercise. You guys are perfectly familiar with pairs, right? If I took a simply typed lambda calculus up there and added pairs to it, type tau 1 cross tau 2, right? And added terms for that, pairs first of E, second of E, with the appropriate typing rules. And then I tried to extend my proof. What would I need to do to the logical relations up on the board? Add a clause to the value rule. Okay, and let's see what that clause would look like. I want to define I want to define the set of values that belong to the pair type. What's the value form for a pair? It's a call by value language, so it'll be pairs of values. All right. So, what do I put here? A pair of V1 and V2. And when should we say that V1 and V2 legitimately belong to our type interpretation? And legitimately here means we wanted them to not get stuck when we run them. What do we have to say about them? They also belong to logical relation. So we want to say that V1 belongs to our interpretation of tau 1, and V2 belongs to our interpretation of tau 2. And that's it. And several cases in the proof. Right. That's the only change we need to make to the logical relation. And then you will have 3 more cases, of course, in the proof of the fundamental property. One for the introduction form, the pair, for the typing rule for pairs, for the typing rule for first, and for the typing rule for second. Okay? All right. Now let's do sums. Yeah.
The relation is preserved under explanation.
Yes. Okay, great question. So here, let's look at all of our value relations, right? All of the definitions for bool, for functions, and for pairs. In some places, remember that thing we call condition 3, that's what you're referring to, that the relation should be preserved under the elim forms for the type. And even yesterday, when we defined Sn for bool, we didn't add anything that corresponded to that third condition. Our proofs just still went through. Okay? Same thing today. I haven't added anything about if to the V interpretation right there. Right? The proofs still go through. That third condition is mostly about functions. We saw how the application case failed yesterday at the beginning of the lecture when we tried to naively push through proof of strong normalization. That's the whole reason we defined a logical relation, so we could strengthen our induction hypothesis. And we strengthened our induction hypothesis by adding that third condition that we talked about, preservation under elim forms. Here's that condition. This is condition 3. So this logical relation does have that property built into it. But the thing is, we only need it for functions. And as you just saw, we wrote pairs. We don't need it for pairs either. And what's the rule for when we do need it? I don't know. Yeah. That. Yes. I could have written this as lambda x tau e, tau 1e applied to v, equivalent. Nothing changes. All right? That's how I wrote it yesterday. You know, I just had an e applied to e yesterday. Okay. So the two are equivalent. All right. So condition 3 is built into the function definition. Condition 3 is not built into the Boolean definition. Condition 3 is preservation under elim forms for the type, is not built into this either. So I'm not saying anything about what first and second are going to do. The reason is that when you run, it has to do with the operational semantics, really. When you run, let's write down operational semantics. What does the reduction rule look like? When you have a first of a pair, imagine this pair to be this pair, right? If I had to do first of that, I would end up with a V1. So intuitively, it suffices that this definition tells us something about the V1. That's all we need. We don't need to say something more. Functions are different. Functions are, there's a contravariance problem. If you don't know what that word means, it doesn't matter. Similarly for second, right? Second of a pair, V1 is going to step to V2. And at that point in the proof, when you do this proof, you'll see that all you need to know about that V2 is that it belongs to V of tau 2, and you'll have it. So it's in the definition. You don't need to say anything explicitly about first and second. With functions, the elim form is basically quantifying over all possible arguments. That's why you get stuck. Right? So you have to say something about those potential arguments and the properties that those arguments have. That's why we need to build that, you know, preservation under elim forms. Very explicitly need to build it into the definition of the logical relation. Otherwise, you won't have a strong enough induction hypothesis. All right, so let's look at one more thing then. What about sums? Suppose I added sum types, tau 1 over tau 2, tau 1 plus tau 2, and I added to my expressions, I added introduction forms in left of E and in right of E, right, for the injections. And I added a case. Case E of in left, let's say X, then do some E1. Otherwise, if it's an in right, then do some E2. Standard case construct. Okay. The value forms of these will be in left of V and in right of V, call by value language. If you want, I can write down the typing rule for case. If anyone wants me to, I'm happy to. If not, let's try and define the interpretation for sums. Same sort of things. Just put yourself in the position where you're trying to say, what are the values of a sum type that belong to our value interpretation of tau 1 plus tau 2? What do we need to say about those values? So what are the values? First,
something or in right something.
okay, so it's going to be in left of some V, or it's going to be in right of some V. Now, what do we need to say about those V's, perhaps? What property, ignore the in right for a second, what property does this V need to have? It needs to be in V of tau 1, right? Okay. It's a union of in left values and in right values, right? And what property does the in right V That value you have to have. Needs to be in V of tau 2 because it'll have type tau 2, right? Now, main question. Do I need to say something about the elim form case and how it would behave? Guesses?
Yeah, because we need to know something about U1 and E2 that are default in.
Okay. It does seem that way. So we're going to go down a road, all right? This is a digression, but how would we say it? That's your next challenge. If I had to say something here about case, what would I say? That when I do a case of an in left of V, what happens? What would I say? How would I say it? Yeah, you're sort of quantifying over all possible continuations in some sense, right? Any other expression. But what will we, I mean, if we wanted to say something about that, we'll have to say something like, for all, let me call it E1, so we remember that it's this branch. So for all E1s that belong to E of some arbitrary type tau, right? Because the result of a case, just like the result of an if, is an arbitrary tau. Has nothing to do with the sum type itself, right? Okay, so we don't know what this tau is, but we'll have to say something like, for all E1s that are well behaved, something like, if I take that E1 and I use V for X in there, let's call this V1 and V2 just to make our lives a little simpler, all right? If I use V1 for X in there, then what? And this isn't even right? Because this has a free variable in it. Oh, wait, so let me rephrase. For all, I'm asking. You see that we're getting stuck? One really major source of concern is that we are trying to talk about all possible expressions with some result type. That tau is popping up completely out of the blue. It has nothing to do with the type that we are trying to interpret. We have a well-foundedness problem if we try to do this. Okay? Now I've gone down. Now the answer for sums is that you don't need to say anything about the elim form. The proofs are still going to work. But I did this exercise precisely to show you this kind of pattern emerges for a few different constructs. And it's instructive to see here that you never want to try to add something to your definition where you are being forced to talk about the interpretation of an arbitrary type tau. It's going to make your relation ill-founded, and there's surely something else sensible that you can do. All right? That's the thing to be on the lookout for. Okay. So, sums, we don't need any of this other stuff. It all works out with just that definition. Yes? Okay. Yeah.
So, basically, the only thing I should think about when deciding what is the logical relation for a type like what for the D
yeah.
Is what are the values of the type. And so the only reason we cared about the elimination form and the one for functions is that something's not a function unless it takes the input to the proper output.
Exactly.
Okay.
Yeah. And the function case actually has to do. The function case is sort of the heart of the logical relation. And this is a good moment to mention the slogan for logical relations, right? Logical relations come with the slogan that they will always take related inputs to related outputs. Actually, I mentioned this yesterday, didn't I? Okay, let me repeat it. See this here? This is our sort of topmost level logical relation definition, right? That's what we're proving in the fundamental property, that if something is well typed, then it's in the relation. Let's read this. What is it saying? Here's what it's saying to me. It's saying, if you give me inputs with the property of interest, then I will give you an output with the property of interest. When you do binary logical relations, where we will have two terms, we will have an E1 and an E2 that are equivalent here, for example, then you want to read it as, if you give me related inputs, then I will give you related outputs. That's what will happen, right? But still, it's, so the standard notion, the standard slogan is, for logical relations is that if you give me related inputs, I will give you related outputs. And the heart of where that is happening is the function case. It's saying, if you give me an input for my function which has the property of interest, then I will give you an output with the property. Okay? And that's the pattern in every single logical relation you will work with or try to define. Okay, so type safety pairs sums. Now let's move on. Okay, so I want to talk about recursive types now. Let's just think about recursive types. So recursive types are useful for defining data types like lists and trees and streams and so on. Once you have recursive types to your language, you should also be able to, your language will have to be non-terminating as well, right? Okay, so we should be able to type check a term that diverges. Have people seen, when I say omega, how many people know what that is? Okay, I will explain it. All right. Okay, maybe that's a, let's start there. Okay, so if we are not in the simply typed lambda calculus, if we are in the untyped lambda calculus, we can write a term that diverges. Lambda x, x applied to x, applied to lambda x, x applied to x. Notice that I am not in the simply typed lambda calculus. I have not put a type annotation here for my variables. This term is called omega. Run this term in your head. What happens? Yes. So it's a function being applied to another function. We take that function, we substitute it in here for these two occurrences of x, and what do we get? Omega itself again. With every single step, this term just reduces to itself. It loops forever, right? This term is perfectly fine in the untyped lambda calculus. In the simply typed lambda calculus, it is not a legitimate term. It does not type check. In order to make it a simply typed lambda calculus term, we need to put a type annotation over here. So, can you guess what that, if we're in the simply typed lambda calculus, can you try to construct a type? Even just for one part of these two, right? For the self-application. It's a conundrum, right? This thing needs to be a function, so maybe I should make it a function type. But this thing needs to be a tau1. It just won't type check. So in the simply typed lambda calculus, that is the reason that all terms terminate. We've already proved that, right? Yesterday, right? And in particular, this is not a well-typed term. All of our well-typed terms will terminate. Okay, so we're going to add recursive types now. And after we're done adding recursive types to our simply typed lambda calculus, we'll see how to write a term that essentially behaves like this, but we'll be able to write down type annotations for the end. We'll be able to type check. All right, so we'll come back to omega in a bit. So recursive types. So in a language like ML, we might want to define, let's say, trees. And we could do that with, just something like a type of a tree. It's either a leaf, or it's a node. I'm going to define trees with integers in the nodes. Int paired with tree. Right? You can define a type like that in OCaml. In Java, you can define some sort of class for a tree where you have some sort of int value right, corresponding to the integer here. And then you have left and right trees. Right, so we can do this in our programming languages. We can't do this in our simply typed lambda calculus. Let's try to sort of figure out what we would want in our simply typed lambda calculus. Well, we'd want something like, what we want to define is a type tree, right? For leaves, we have, we don't care. It doesn't really carry any information, so we could use unit to represent a leaf, right? So we could try to define something like this, where we have tree is either a unit, or we can use a sum type to say that a tree is either a unit or it is a node, right? So unit corresponds to leaf, or it is a node. And it is a node of a pair of an int and a left tree and a right tree. Right? So this is something like what we want, but we can't write. We can't specify. This is an equation that tells us what we're interested in, but the problem is that we're trying to define a tree, and tree appears right here on the right-hand side of this equation, right? It's not a definition. It's self-referential. Okay, so what could we do instead? Well, let's sort of examine this. What do we really have in mind? I'm going to write alpha, use a type variable, alpha, for tree, because tree is this type that we want to define, right? I'm just going to use a stand-in for it. So really what we're after is something like alpha is equal to, let me start writing 1 for unit. It'll just be shorter. Okay? 1 is often used for the unit type. Yep. All right. So basically what we're after is something like 1 int alpha cross alpha. Right. I didn't do anything other than replacing the word tree with the type variable alpha. Tree here was a type, alpha is a type variable, a type name, if you will. Now, the thing that we really have in mind for this equation is that alpha is a tree, this thing is a tree, this thing is a tree, where we are taking the tree that we have up here and plopping it in for both occurrences, substituting it for both occurrences of alpha right there, right? It's just very long to write. So what did I do? I took the occurrences of alpha in here and substituted the entire definition for them in those two spots. All of these things are equal. This is a tree, this is a tree, this is a tree, and I could keep going. I just don't have more board space, and I don't want to write it. Okay, so there's an infinite system of equations, right? Where with every single step, if we keep doing the substitution, we keep expanding the type. They're all legitimate trees. They're all finite type expressions, right? They're just getting deeper and deeper, so to speak, right? They're getting bigger and bigger. But they all correspond to the notion that we have in our heads of what a tree should be. If we take the limit of this process, what we end up with is an infinite tree, right? And that thing in the limit of the process, that infinite type, is the tree that we conceptually have in our mind, right? So what we need, and that thing in the limit of that infinite tree in the limit of this process, is the fixed point for this recursive equation. That fixed point is the notion of a tree that we are interested in. All right? So basically we have a recursive equation, and we're trying to find a fixed point. Right? Okay. So let's make this a bit more formal. So if we so since the definition of a tree is recursive, and we want some sort of a fixed point, let's define a function. All right? I'm going to define a function f whose fixed point we need to find. And I'll write it like this. This is not part of any type. I'll explain this in a second. So this is just a function that takes some alpha. Obviously, it corresponds in my head to that alpha up there. And then gives us back something that corresponds to our tree type. So this is the function I would claim whose fixed point we want to take. All right? Now, what is the definition of a fixed point? If I want to take the fixed point of a function f, let me posit for a second that t is the fixed point of this function f. Then by the definition of a fixed point, t should be equal to f of t. That is the definition of a fixed point. All right? The fixed point of a function is something such that when you apply the function to that thing, you get the thing itself, right? It's some t such that f of t is equal to it. That is what a fixed point is. All right? Okay, and this corresponds to what we're saying, right? The tree that I have in my head corresponds to this function f applied to the tree that I have in my head, right? Okay. So, basically, tree then should be equal to f of tree, right? If we could, so what we want is to take the fixed point of this function. Let us posit the existence of a fixed point type constructor, all right? That's going to solve these equations for us. And I'm going to say that if f is a function, so f is a function f of alpha, right? Then we're going to say that the fixed point of this function is written as mu alpha f of alpha. So I'm positing the existence of a fixed point type constructor, all right? It's going to find the fixed point for us, and that is what this mu is, all right? Now, basically I'm adding a new type to my type language, right? But let's sort of understand its properties a little bit better. What we basically have then, if this is the fixed point finder or the fixed point constructor, right? Then what that means is that this is my fixed point, which means that that should be equal to f applied to my fixed point. Correct? By the definition of what a fixed point is. All right. Now, to make this look a little bit more like types, let me write tau, an arbitrary tau, for f of alpha here. Right? So then what do we have? Basically, I'm saying we have mu alpha tau is equal to f applied to mu alpha. F of alpha I'm writing as tau. Correct? I've just abbreviated the f alphas with taus. So mu alpha tau, which we will see in a second is a recursive type, is equal to our particular f that's on the board right now applied to mu alpha tau. And if we carry this further, right, tau stands for f of alpha. Therefore, this expression is really just equal to tau with mu alpha tau substituted for the alpha in there, right? Agreed? Ask questions. All right. So all I've done is taken this equation, taken the liberty to abbreviate f alpha to tau. That gives me mu alpha tau, and I've copied down f of mu alpha tau. But now I had said that tau stands for f of alpha. That means that if I take that, what I want to do here is f is being applied not to an alpha, but to a mu alpha tau, right? So that corresponds, this whole thing corresponds to taking tau and replacing the thing in there, the alpha in there, with mu alpha tau. And that is exactly what I've written on that side. Correct? All right. Now, ignore the thing in the middle and look at that. So, we are going to add to our simply typed lambda calculus a type of the form mu alpha tau, where in this tau expression in here, alpha can appear free. All right? This is then a recursive type, and we can shift our view from a recursive type, mu alpha tau, to an expanded version and sort of contract back. This is called unfold the type, expand it out, versus folding it. Let's see how that applies to our tree type right here. Our tree type can now be written, so tree can now be defined as mu alpha this, which is just this, unit plus int paired with alpha paired with alpha. Once I give you new types in your language, you can define a tree type. This will be a perfectly legitimate type to write down. It is a recursive type that represents the type of trees that we have in mind. When we want to work with something like this, which represents a tree, we're going to have to do something though. What we want to do when we work with an expression with this type is we want to get under that mu, right? We want to figure out if the type is actually a leaf, or if the value that, so suppose that we have an E that has type tree, as in has this particular type, right? How will we get our how do we check whether the E, or we can call it a value if you like, how do we check that the E is a leaf or a node? Well, we're going to do an unfold. We want to unfold our view from this type to the expanded type. We want to go from here to here. Let's see how we do that. So we're going to go from here to take this tau unit and substitute the whole thing for the occurrences of alpha. So we end up with mu alpha unit plus int cross alpha, and then same thing again. Probably missing a paren at the end. Okay, so mu alpha tau gets turned into tau with mu alpha tau for alpha. That's our unfolding of our view, if you will. And to go back, if we're done sort of inspecting a tree, now, once we unfold something, we can actually apply case to it. And we can check, is it an in left or an in right? If it's in left, then it corresponds to a leaf. If it's an in right, then it corresponds to the node. Right? And once we're done working with that part, we can fold the view back again to get back to just the original tree type. That's the intuition. All right? So these types that we're introducing, recursive types, these are called iso-recursive types. There's an isomorphism between the type mu alpha tau and its unfolding, which is tau with mu alpha tau substituted for all the alpha occurrences. Right? So there's an isomorphism, and to shift views, there's an isomorphism between these two types. And to shift views, we have syntactic constructs in the language which we use to shift our view from this type to this type and back again. All right? So with that in mind, let's go and formally add these constructs to our language. So our simply typed lambda calculus is now going to have these type variables alpha, and it's going to have recursive types mu alpha tau. To our expressions, we are going to add two forms, fold of an expression, and let me erase the if then I'll take up space. So we're going to add fold of E and unfold E. Those constructs that I said will shift our view back and forth. Our value form here will be fold V. It'll be something that has a recursive type. We'll see the typing rule in just a second. Actually, let me do the typing rules first, and then we'll edit the operation semantics. So here are the typing rules that we want to add. Fold is what introduces a recursive type. So fold of E has type mu alpha tau if E has type tau with mu alpha tau for alpha. And unfold is the elim form. So unfold of E, if you give me some E that has a recursive type, mu alpha tau, then unfold of E shifts the view to tau with mu alpha tau for alpha. Okay? So with this basic construct, we now have the ability to define trees and lists and any other recursive types that we want. And we have the ability to type check omega now. Okay? So just to talk about lists for a second, how can we define lists? Suppose I wanted to define an int list. How would you define, how are integer lists represented? They are either nil or cons, right? How do you want to represent a nil? Okay. So we can use a recursive type, mu alpha, 1 plus integer paired with more list. Right? The alpha here represents our int list, so to speak. And here we're saying that it's either nil or it's a con of an int and the rest of it. All right. Do you guys want to see how to type check omega, or should we stop? We can do that tomorrow if you like. Let's do it? Okay, cool. All right. So, omega. So lambda x, x, x. Lambda x, x, x. We want to find a type annotation that we can put down right here. Of course, your hint is you're not going to use recursive type somehow, right? Okay. So let's just focus on one of these two, right? Let's call it self-application. And we want to figure out what type to put here such that this type checks. Right? Okay. So what might we do? We know that x needs to be a function, and then it needs to not be a function. So needs to be a function, right? So it needs to, this x right here, it needs to be some sort of a function that returns something. But what does it take? What is the argument of the function? Like if we focus our attention on this x for a minute, it needs to take itself, right? Itself. So if we're trying to use itself, it seems like a good hint for recursive types. Just like with trees, right? We were trying to say, hey, we're trying to represent the tree itself is represented by alpha. So we're going to start with a mu alpha and say what we really want is a function that takes itself as the argument and returns, I don't know what it returns. Let's just say it returns some tau. Some tau. Okay. Let's see now. Is this going to work? Actually, let me try to do. Okay, so here's our conjectured type, and let's try to see if we can write down something that type checks. So if we try to make this okay. Well, this is a function that takes a mu alpha, alpha arrow tau. That means, wait, but this guy is a recursive type. It's not a function. I can't apply it. I need to turn it into a function. I need to shift views, right? If I unfold this first x, what would I get? I would get this type substituted in for this, right? So we would get tau with this type substituted for alpha, which is, right here, we're going to put mu alpha, alpha arrow tau for the alpha, sorry, tau, and arrow tau. Correct? Okay. And the type of this guy is still the same. Mu alpha, alpha arrow tau. So now does this type check? If I wrote out, I won't write out the entire typing derivation, but basically we're taking an x, which is a recursive type, we're unfolding to shift views to the expanded type. This is, you see how I got this, right? This is just my body of the mu, which is alpha arrow tau, with mu alpha, alpha arrow tau substituted for alpha. That is that. So we shifted views. We shifted from one view to the other. And conveniently, we only did it in one space, one spot, not the other. Right, so that type checks now. So all we have to do to that expression up there is essentially annotate x with this type and then unfold. But what is the type of this whole self-application thing? type does it have? It's a function. It takes one of these. So let's write it out. Right? And gives back. It gives back. Right, it's this function taking that, so it gives back a tau. So that is the type of this entire expression. Now let's shift up. We have to still type check omega, right? Okay. So we have edited these. We're basically saying, I'm just going to write SA. Yeah, now we want to do SA applied to SA, right? Self-application, this entire function applied to itself. But aren't we going to have a problem? That's the type of SA. It is a function. That's good. This guy needs to be a function, so it can have this type. But this guy needs to be of argument type, right? How do we get the thing in this position to have type nu alpha, alpha, or tau? Fold it. We just type checked omega. All right? And when you run this omega using the operational semantics, oh, damn, I forgot one rule. The operational semantics, when we do an unfold of a fold value, we get back the underlying value. All right? So given the operational semantics on the board, if you try to run that term up there, it will behave exactly like the untyped omega does. It will diverge. Yes?
Do you need to do capital E cases also?
Yes, I do. Thank you. So we'll call by values. So we're going to evaluate in these positions. So we're going to add an evaluation context which says evaluate under the fold till you get to a value, and evaluate under the unfold. Okay? And that's when this rule kicks in. Okay? Yes? The type tell us that the term diverges. Yes, yes, absolutely. That is, I wanted to mention that. Yeah, thanks. Notice how we've picked an arbitrary tau here, completely arbitrary. It could be anything. It could be bool. It could be a function. So that's the surest sign that this term will never terminate. You know, it's going to loop forever. We can assign any result type to it, and it'll be perfectly fine. Right? Okay. All right. Stop there. We'll continue tomorrow with how to do logical relations for recursive types.